configuration of B2 molecule. Okay. So if I'm going to have the electronic configuration of B2 molecule, diboron. Okay. So if we are having this one, so what type of electronic configuration we have? The general electronic configuration of boron is 1s2, 2s2, 2p1. Hmm? Hmm? And you know that in molecular orbital theory, z-axis is considered to be as internuclear axis, means z-axis is going to make sigma bonds. Okay, so we have sigma 1s2 because, and then anti-bonding sigma 1s2, then 2s2 sigma 2s2, then anti-bonding 2s2. Okay, then the pi p1 is going to make means this is 1s, this is 2s2, and this is 2p1. So this is going to make the pi bonding. Okay, so this p is going to make pi bonding, so we'll consider this one is x. Okay, so this is going to make x, px is 2p. Okay, 2px, and one is 2p. You know that if the two electrons are participating, then or you can make it like this way. If we are going to have like this 1s orbital here. Okay, this is 1s, this is 1s, so they will make sigma. This is molecular orbital. Okay, sigma 1s. Okay, 1s, and this is anti-bonding sigma 1s, and this is going to have two electrons because we need to fill 4. Okay, so this is the first one, and how the second one we will fill. The 2s2 will be similar, 2s2 here and 2s2 here. This will form anti-bonding for sigma bonding 2s, and then we will have anti-bonding 2s. Okay, then here the two electrons are there, 4, so we will fill 4 like this way. Got it? But now the last one is p. Okay, and we have p orbitals, and we're going to have only one electron in its outermost shells. Okay, got it?
Yes.
So if we have px, 2px, 2py, and 2pz, here we have 2px, then 2py, and then 2pz. So first the pi bonds will be formed. So here we will have, and in this one we're going to have like this. Okay, we'll have the two same here. Okay, in B2, and then we'll have this one. Got it? Like this way. And similarly, this is same for all. We'll have this one. Okay, now this is not being required. Okay, so no space here, so under. Okay, so we'll have only XX, one electrons here. So one will fill here, one will fill here. So this is pi 2 pi 2px. Okay, and pi, got it? You understood? Pi 2py. Okay, got it? And there will be no electron in sigma 2pz. 2pz, there will be no electron. So this type of electronic configuration, you understood?
Yes, sir.
Yes.
Okay, now moving to the next one is if we have more than 14 electrons, then in that case the electronic configuration is like we'll have in the if we are having more than 14 electrons. Okay, so here we'll have first 2pz at the end. Okay, and then this one SS is same, but here in the previous one we were having like this and this one, but here we're going to have like this. Okay, like this, and the similar, the same. This is same for all. The above one is same for all. Got it? Got it?
Yes,
So
sir.
let's you do the electronic configuration of let me help you. What's it? Let's start with the applications. Oh, I have not shared my screen and I'm just teaching you continuously and you are saying
Sir, you have shared your screen.
I shared my screen.
Yes.
Yes.
Then it stops.
No, it didn't stop.
How long it had been is that I was teaching you without sharing my screen?
Sir, your screen was already shared. It was not in full screen.
Is it showing it? I'm write something here. Like I'm writing applications of, is it visible to you? Applications
Yes, sir.
Yes.
of MOT. Applications of MOT. So what is the application? First of all, the first applications of molecular orbital theory, that molecular orbital theory is used to determine the bond order. Okay, means bond order means double bond, triple bond, single bond will be there. So it is used to determine the bond order. You understood? So first application is molecular orbital theory is used to determine the bond order. The bond order. Okay. The BO here is bond order. We'll see that NB minus NA divided by 2. You understood? Okay. What is NB and what is N NA? This is the number of electrons. NB is the number of bonding electrons. Number of bonding electrons, and Na is number of anti-bonding electrons. Okay, anti or number of electrons that are present in in anti-bonding molecular orbitals. Okay, understood?
Yes, sir.
Number of anti-bonding electrons. Okay, for example, if I'm talking about that bond order of helium He2 does not form He2 because it is a noble gas. Okay, so He2. So why does helium does not form He2 molecule? He He2 molecule. Why does it does not form? So let's talk about this one. Why bond order is 0? Bond order 0 means there is no bond between the two. Okay. So if I'm talking about the bond order here, so let's talk. That is bond order of helium. Okay. He2. So for example, helium is going to have electronic configuration 1s2, 2s2. Okay. 4 electrons total. So you will see here, and here is another atom 1s2, 2s2. So when 1s orbital is going to combine, so 1s2, 1s2, they are going to combine. So here are 4 electrons total. The 4 electrons will be shared like 1, 2, 3, 4. These are the molecular orbitals. This is sigma bonding 1s2. This is anti-bonding sigma 1s2. Okay. So here the total number of electrons in bonding and anti-bonding is same. Okay. Next one is if similar for the 2s also. So since the number of electrons in bonding and anti-bonding is same here, so we'll say that the bond order is 0. Okay. Got it?
Yes, sir.
Got it? So if I'm talking about the electrons, so we'll say here that bond order is equals to 2 minus 2 divided by 2 is equals to 0 by 2 is equals to 0. So since the bond order is 0, so we can simply say that. Okay. We can simply say that it's bond order. Since bond order is similarly, why bond order of C2? C2 means carbon. Why does carbon does not form C2 molecule? You have seen O2 molecules. You have seen carbon can form like this 1, 2, 3, 4. Okay. So it can form, it can make bonding of 2 electrons or 3, 4 electrons. So why does it does not make? Similar reason is for this one. If we do the electronic configuration of carbon, C2 molecule, the total number of electrons will be 4 for this carbon, 4 for this carbon, and 4 for this carbon, the outermost shell's electrons. Okay. And the total number of electrons are 6. Okay. the total number of electrons of carbon is going to have how many electron? 2,6, 2,4 electronic configuration. So total number of electrons one is 6. Okay, you understood? So for two carbon atom, we're going to have 12. Are you getting my point?
Yes, sir.
Yes.
So for now, if we are just going to write the electronic configuration for the electrons that are going to have less than 8 electrons. So if any element is going to have less than 8 electrons, what is electron configuration? 1s2. Don't write 1s2 first, write 1s. Okay, then again 1s, then 2s, then again 2s. Okay, then then if you're going to have the less than 14 electrons, then we have 2px, 2px and 2py bondings. Okay, 2py and then 2p, like we have like this way. Okay, 2px, 2py, and this is pi. This is also pi, and then we have sigma 2pz, sigma 2pz, like this way. Okay, got it?
Yes,
Got
sir.
it? And then we will have like this way. We'll have like this way. Then what's the value of this one? We're going to have 2p is antibonding, 2pz. Then we'll have antibonding, 2py, 2py, and antibonding 2pz. Okay, so here sigma, then antibonding, sigma, 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 antibonding. Okay, so now if you fill the electron configuration of 12, total 12 carbon, total 12 electrons. So to 1, 2 to 4. Okay, 2 to 4. Got it? 4, 4, 8, 8, and then we will have 1 here and 1 here, 1 here and 1 here, then 1 here, and then again 1 here. Okay, got it?
Yes, sir.
So we will have 2p here and 2p here. Okay, got it? Y2
Yes.
here. Okay, and then we'll have 0 here. Got it? So if we consider the bond order of CO2 molecules, so here the anti-bonding, this will cancel out because they are cancelled. Okay, or you can cut it if they are same. You can add it. Otherwise, you have to check this one only. Okay, these are the bonding electrons. Okay, so if you count the total number of bonding or anti-bonding, you can count it. In the bonding, we have 2 to 4, and here it is. They are also in the bonding. 2 to 4. Okay, and this one is 6 to 8. Okay, so we're going to have 8. Okay, so 8 in the bonding. You understood? Understood? So 8 in the bonding.
Yes, sir.
And how many electrons are there in the anti-bonding? 4. Got it? So how many are there? 4. So you will divide by 2. You will get 8 minus 4. You will get how much? 4 divided by 2. You will get 2. The bond order is 2. Are you getting?
Yes.
Okay. Now calculate the bond order of oxygen. Calculate the bond order of oxygen. Calculate the bond order of oxygen. What is the bond order of oxygen? So what's the bond order of oxygen? Total number of electrons, tell me. Total number of electrons, 16. 2 from this, 8 from this oxygen. Electron configuration 2, 6. So, are you getting my point?
Yes.
Yes.
Okay, so we're going to have 1s, 1s, then 2s, and it is greater than 16. So 1s, 2s, 2s. Okay. Okay. So we'll have 1s, 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 2s, 2s, then what? Tell me. Next one is
Pi to px and pi to py.
no, it is more than 16. Then we will have sigma 2pz. Okay. Then pi 2py and then pi 2px. Okay. So in if the electrons are more than 16, then we're going to have the electrons are more than 16, then we'll have this one, otherwise this is going to be there. Okay, got it? If it is less than 14 or equal to 14, then it will be here. This they will come first. Okay, but if it is greater than 16, it is going to be like this. Okay, this is pi, sigma here, this is sigma, this is sigma, this is sigma. Okay, now we're going to have anti-bonding. You can have 16 electron 2, then 4, then 6, then here we're going to have 8, then 2, 8. Okay, like this. Okay, and then we're going to add here, sorry, we're going to add here 4 electrons. So 2 here, 2 here, like this. Okay, 1, 2, 3, 4, 5, 6, 7. 7 to the 14 is here now till now. And then we'll have anti-bonding. So anti-bonding will have, anti-bonding is same for all. Okay, this one, and then we have 2. Okay, this is, so this is sigma. Okay, anti-bonding, and 2pz. Okay, got it?
Yes, sir.
No, no. It is going to have so if in oxygen, if it is greater than this one, so this will be like this. Okay, so if now it will be anti-bonding, so anti-bonding means pi, then 2p x, and then 2p y. Okay, then how many electrons were remaining? Only 2. 14 has been done, so 1 for this one, 1 for this one. Okay, got it?
Yes, sir.
Yes.
So count the total number of bonding and anti-bonding electrons. So this is sigma, this is bonding, this is anti-bonding, this is bonding, this is anti-bonding, this is bonding, this is bonding, bonding, then anti-bonding. Okay. And this is 2p z 0. So 2, 4, 6, 6, and 4, 10. And anti-bonding, how many we are going to have? 2, 4, and 2, 6. Divided by 2, you will get 4. Divided by 2, you will get 2 bond order. Okay. Got it?
Yes,
Yes.
sir.
So the bond order of oxygen is 2. Got it?
Yes.
Yes.
Calculate the bond order. If I'm talking about the bond order of O2 positive. O2 positive means 1 electron is left, not here, but we will have 15 electrons only. Okay, 15 only. Understood?
Yes, sir.
So if we have 15 electrons only, then how will we do? 2, 4, 6, 8, then 10, then 12, then 14, and then 15. So this will be removed. Okay, this will be 0. Got it? This will not be going to have. So we'll have how many bonding? We'll have bonding as 10 and anti-bonding will going to have 5. Okay, 5 divided by 2 will have bond order as 2.5. Okay, the bond order can be in decimals also. Got it? So if we have O2 positive, then we'll have bond order 2.5. You understood?
Yes.
Okay. Now moving to the next part is molecular orbital theory is used to compare the bond length. So we can say that if there is more bond length, okay, we can say that if there is more and more number of bonds between two atoms are there, then we'll say that you'll have less bond order. Okay, so bond length is inversely proportional to if there is more bond. For example, if the two atoms are combining with 3 bonds, so they will have bond length, means the bond length between these two atoms will be less because they are tightly bonded. Okay, got it?
Yes, sir.
Third application of this one is that molecular orbital theory is used for comparing the bond energy or bond strength. Okay, is used for comparing the bond energy and bond length. Okay, so it is also used for comparing the bond energy and bond length and stability. Understood? Got it?
Yes.
So we'll say that how does bond stability? So we'll say that if there are more and more, if there are lesser number of anti-bonding molecular orbitals or number of electrons are less in anti-bonding, then the stability of bond will be more. Okay, so we can say that stability is inversely proportional to number of anti-bonding electrons. Okay, got it? So if I ask you that which is more stable, H2 is more stable, and Li2 is more stable. So in H2 we have how many electrons? Total electrons we have 1 hydrogen, 1 for this one, we have 2 electrons only. Total electrons we have 2. How many electrons we have? 2. Okay.
2.
So we will have 1s2 sigma, and then we'll have anti-bonding 1s0. So here this is going to have in bonding it is going to have 2 electrons, but in anti-bonding it is not going to have any electrons. But if I talk about the lithium is going to have 3 electrons in outermost shells. So the total electron 3. So total number of electron is 6. Li2 if I talking about, so lithium is going to have 2, 1 electron configuration. Total number of electron is 6. So 1s2, then anti-bonding 1s2 sigma anti-bonding. Okay, and then 4, and then we're going to have 2s2 sigma 2s2 sigma 2s2. Okay, so here how many electrons? There is 1 bonding, 1 anti-bonding. Okay, so if I talk about that, the bond order of this one, the Li2, and if I talk about this hydrogen, is both are going to have bond order 1. How can we say that both are going to have bond order 1? Number of bonding electrons 2 and anti-bonding electrons 0 divided by 2, you will get 1. Here number of bonding electrons are 4 minus anti-bonding electrons 2 divided by 2, you'll get 2 divided by 2, you'll get 1. Okay, but you will find here that the H2 is more stable than Li2. Both are going to have bond order same, but here we will say that here the anti-bonding electrons here is 0, but here the anti-bonding electrons is 2. So if there are more number of anti-bonding electrons, if the bond order is same, then we will compare the number of anti-bonding electrons. You understood?
Yes, sir.
Yes.
Okay, so here is noted down if the bond order is same. If the bond order is same, then if the bond order is same, then Then we will compare the number of anti-bonding electrons. Okay, we'll compare anti-bonding electrons. Got it?
Yes.
Yes, sir.
So we'll say here, okay, if lesser than anti-bonding electrons, lesser the number of anti-bonding electrons, okay, greater is the stability. Greater is the stability. Understood? Understood?
Yes, sir.
Okay. So if I talk about the paramagnetic and diamagnetic nature, so it also gives us the idea of which is going to have which element is going to be paramagnetic in nature and which is going to be diamagnetic in nature. Okay, diamagnetic. So molecular orbital theory gives us the idea of if the electrons is going to be have means if an element is going to be, or if a molecule is going to be paramagnetic in nature or diamagnetic in nature. So paramagnetic means if it is going to have more number of unpaired electrons, then it is paramagnetic in nature. For example, if I talk about the oxygen, so oxygen is going to have 16 electrons in its outermost shells. Sorry, total of 16 electrons in O2. In O2, I'm talking about. Okay. So if you do the electronic configuration of oxygen is 1s2, then 1 sigma 1s2, then antibonding sigma 1s2, then 2s2, then sigma, and then antibonding 2s2. Okay, then we'll have pi. Okay, or then we'll have this is more than 16, so we're going to have sigma 2pz, sigma 2pz, and then we'll have 2px and 2py, and it will be pi. Okay, and then we'll have antibonding 2px, antibonding 2py. Okay, and this is bonding, this is bonding, this is bonding, this is antibonding, and this one is also antibonding. Okay, got it. So if I fill this 16 electrons, 2, then 2, then 2, then 2, 8, and then 2, 10, and then 2, sorry, 1 here, sorry, 2 will be filled here, means if it is like this. Okay, so we'll fill like this. Okay, so 2 here, then 2 here. So here, if I'm going to talk about that, here it is 2, then 2, then 2, then 2, then 2. Okay, we're going to have 2 to the 4, 4 to the 8. Sorry, here we'll have 4, then 4. Okay, this is 8, then 10, and then how many? 10, and then 14, 14 and 2, 16. Okay, so if we 16 will be filled like this. Okay, so here you will see that this is going to have unpaired electrons in antibonding molecular orbital, then it is going to have unpaired electrons. So if there is unpaired electrons are present, so we'll say here that if the unpaired electrons is present, it is paramagnetic in nature. You understood?
Yes, sir.
Yes.
So if it is unpaired electrons, if it is fully filled is there, every orbital is fully filled, then it is diamagnetic in nature. Okay, and if it is going to have unpaired electron, then it will be going to have. Okay, so I'm going to write here. Here the bond order of oxygen is 2, you know. Okay, so if the bond order of oxygen is 2, got it? Then here whether it is going to have bond order 2 or something different. But if I talk about this one, that if we do the electronic configuration, and if we are going to get the unpaired electron in that one, that it is paramagnetic in nature. Got it?
Yes.
Okay. So now moving, next one is molecular orbital theory diagrams. Let's explain you one more time. Diagram. We'll say that arrangements of atomic orbitals, bonding, molecular orbitals, and anti-bonding molecular orbitals. Okay, according to their energies. Note it down. Is called molecular orbital diagram. Done?
Yes, sir.
The same that we are studying here, it is the same. If you draw the diagrams of N2, then how can you draw the diagrams of N2? So it is drawn like this. Okay, N2. So if you're going to draw the diagrams of N2, so the energy of, you know, that will have 1s2 orbital first, 1s2. Then here it is also 1s2 orbitals, okay, and they are going to combine together. This is one nitrogen, this is another nitrogen, so 1s2 electrons for both. So here we'll have, first we'll have this electron configuration like this way, okay. Then we have 2s2, okay. We draw it like this. Okay, then again we'll have N2, electronic configuration 2p3. Since the electrons are less than 14, they are 2p3. Okay. So since the electrons are less than 14, so what we'll do if the electrons are less than 14, we'll have this type of arrangements. Okay. Got it? Then here is 2px, 2py, 2pz. Here it is 1, then 2, then 3, then 4, then 5, then 6. Okay. Got it?
Yes, sir.
Okay. So you can easily say that here the bond energies, the lowest energy of this orbital, then this one, then this one, then this one, and this one, then this one. Electrons are moving from lower energy level to the higher energy level. Got it?
Yes.
Okay. Now you can easily calculate means there is an easy way to calculate the bond order. Okay. So calculation can be very easy. For example, if you need to, this is if you need to calculate the bond order of this one. Okay. Okay, so if you are going to calculate the bond order of this one, so you can easily cancel out this one. For example, if you are having the electronic configuration of this one, if I write it, so no need to calculate the whole, but just you need to find out the number of antibond. If they are canceling out each other, then it's okay. So for example, if it is sigma 2s2 and then antibonding 1s2, then 2s2, then antibonding 2s2, so they will cancel out each other. Okay, they will cancel. No need to add and subtract these. Only calculate only calculate the unpaired electrons here. So you can see here that here this will cancel out with this one, this will cancel out with this one. Okay, just you need to check it, this one. So here the bonding electrons are 6 and the anti-bonding opposite to this one is 0. So you'll get set 6 minus 0 upon 2, you can get 3. The bond order is 3. Got it? Got it?
Yes.
Okay, now if you are going to have the different kinds of atoms, for example, if I'm having CO, carbon monoxides, okay. So if I'm talking about this CO, then what is the bond order of CO? Bond order of CO. So how many electrons are there total? 6 for this one, 8 for this one. 6 for carbon and 8 for oxygen. Total 14. So if you do the electronic configuration, how will you do? 1s2 sigma, then anti-bonding 1s2, then 2s2 sigma, then anti-bonding 2s2, then this is less than 14. So we'll have first 2p x and then 2p y, and this will be pi, this will be pi, and then we'll have sigma 2p z. Okay, then anti-bonding 2pz is 2pz, then anti-bonding is. So if I'm talking about this one is, if I'm going to calculate the electronic configuration, so how will you do the electronic configuration on this one? So if I talk about CO positive. So if I talk about the CO positive or CO is 14, CO positive, you can have, means if I'm talking about the isoelectronic species, for example, if I'm talking about the electronic configuration of nitrogen is nitrogen is going to have 14 electrons in total, and two molecule is going to have 14 electrons in total. Okay, and CO is also going to have 14. So if they are going to have the same electrons, then they will have the same bond order. Got it?
Yes, sir.
You understood what I'm saying here? For example, if nitrogen, if you don't know the bond order of CO and it is being asked to calculate, so don't calculate it. Calculate the total number of electrons. Carbon is going to have 6, oxygen is going to have 8, so total is 14. So now find the species which is going to have the same bond order. So for the number of electrons, so you're going 14. 14 is also present in the nitrogen also. 7 for this nitrogen atom, 7 for this another nitrogen atoms. So both are going to have 14. The bond, you know, the bond order of nitrogen is 3. So here the bond order of nitrogen, there will be 3. Okay. Got it?
Yes, sir.
So the bond order, if I talk about that, what is the bond order of CO positive? CO positive. So they are 13 electrons. So here you need to calculate. For 13 electrons, you need to calculate. So here it is 2, then 2, then 2, then 2, and then 2 for this one, and then 2 for this one. How many are there? 8, 8, and then 1 here will be 1. 2px. What? Wait a minute. We'll have like this. Okay, like we have 2px and 2py. So we need to here 1, 2 to 4 to 6 to 8 we have done, and we need to fill the 13 total. So like we're going to fill 8, 9, 10, 11, 12, and then 13. Okay, then 2p2 here and then 2p1 to be that here. Okay, so you will fill like this way. Got it? Got
Yes,
it?
sir.
So what's the bond order? So you can easily calculate that there are 5 electrons. This will cancel out with each other. This will cancel out with each other. This will cancel out each other. Okay, then how many electrons are there?
5 bonding electron.
So here is 13 electrons, and you will find the bond order is 5. You will find 2.5. And since it is CO positive, you understood na? CO positive. CO positive means if CO is going to have 14 electrons, then positive means it has loosened 1 electron. So it has 13. Okay, got it?
Yes.
Yes.
So 2, then 2, then 4, 6, then 8, 8 and 2, 8 and 2, 10, 10 and 2, 12, 12 and 1, 13. Okay, so they are all bonding. They are not anti-bonding. They are all bonding. Okay. Okay. Then we'll have 5 electrons in the bonding and anti-bonding 0. So divided by 2, you will get 2.5 as a bond order. Got it?
Yes, sir.
Yes.
Okay. Calculate the bond order of S2. S2. Bond order of S2. Are you calculating? S2 bond order. So how many electrons are there? 32. Sulfur is going to be 16. Sulfur actually, we are just talking about the gases only. Okay, though only the gases molecular orbital theory is applicable. If I talk about this one, that molecular orbital theory show the same behavior for the oxygen, so it is not applicable for those elements that does not exist in the vapor state. Okay, so like nitrogen exists in the vapor state, so it is applicable for the vapor states only. So if it is not applicable for those elements that does not exist in the molecular form, but okay, so we'll say that sulfur if exists in the vapor form, if you heat it, it will show the same behavior as that of oxygen. Okay, got it?
Yes.
But since it exists in the solid form, so it is not applicable. So we'll not say for the sulfur. Okay. So if I talked about that, next question, if I talk, let's have some question. Okay, wait a minute. Okay, here we have question. Which of the following species gain stability, okay, by losing one electrons? One is B2, N2, O2, and H2. A, B, C, D. Which will lose? Which will gain stability by losing electrons, by losing one electrons, more stability? So you know that if we have this B2, okay, so what is the bond order of this one? Tell me. Bond order of B2. Tell me. What is the bond order of B2?
1.
1. Yes. Its bond order is 1. Total number of electrons is, okay, the bond order of B2 is 1. If from B2 if it loses one electron, it form B2 1 positive, then the bond order will be, what's the bond order of B2? You can do is very simple. Here, the electronic configuration of B2, 1s2. Boron is going to have electronic configuration 1s2, 2s2, 1s2, 2s2, 2p1. Okay, 5 electrons total. Similarly for other 1s2, 2s2, 2p. Okay, so this is, if I consider this is bonding, then this is anti-bonding. This is bonding, this is anti-bonding. This is bonding only. Okay, they will cancel out each other. They are the 2 electrons here. So you will 2 minus 1 divided by 1, you will get. But if you lose 1 electrons, okay, if it loses 1 electron, so it will lose from here, and it will going to have only 1 electron, so its bond order will become 0.5.
Yes, sir.
So from 1, its bond order will changes to, from 1 it is 1, but it's here, if it loses 1 electron, it will become 0.5. Okay, similarly, if nitrogen is going to lose one of its electron, then its bond order will become, now it is going to have 3. We have done that N2 positive. N2 positive means 13 electrons, and we have seen in the previous one that, like in CO positive we have seen that is going to have 13 electrons, bond order is 2.5, and N2 positive is also going to have 13 electrons when it loses, so it will going to have, if it become N2 positive, it will have 13 electrons, it is going to have bond order 2.5. Similarly, it is going to have 8 as 8 electrons. The current bond order is 2.5. The current bond order of oxygen is 2. But when it comes to 15, okay, from 60, 15, then it is going to have its bond order as 2.5. It will have its bond order. So when oxygen is going to lose 1 electron, its bond order is increasing. Got it? Here hydrogen will have from 1 to 0.5. So we'll write here that if boron B2 changes to B2 positive, okay, and if N2 changes to N2 positive, and if O2 changes to O2 positive, and if the last one is if hydrogen H2 changes to H2 positive. So its bond order will change from 1 to 0.5. Here the bond order will change from 3 to 2.5. Okay. And here its bond order will change from 1 to 0.5, but in case of oxygen, its bond order will change from 2 to 2.5. 2.5. Got it?
Yes,
Got
sir.
it? So since the bond order is increased on losing the electron, so we'll say that the stability of O2 positive is more stable when it is more stable. Got it? Got it?
Yes.
Yes, sir.
So here we'll see that this will lose one electrons on. Okay. So next question: which of the following species is paramagnetic in nature? Is paramagnetic in nature? A, B2, O2, O2 minus, NH2. Tell me. So you know that bond order is here is 1. Here the bond order is 2. Here the bond order is 1, but here it will have, if it is also gain 1 electron, then it is going to have bond order 1.5. How? You can check. There are 17 electrons will be there because it gains 1 electrons. Got it? Got it?
Yes.
8 I am not representing here for the s orbital. I'm not representing here. This I'm representing the only p orbitals electrons. Okay, so since the total number of electrons are 17s and it is greater than 7, so we'll have sigma 2pz, then we'll have pi 2px, pi 2py. Okay, so 8 we have already done. Then how many remainings? 11s are remaining. Okay, got it? Since, sorry, 9. 8 I'm not writing for 1s2 2s2 2. Okay, so I'm not writing for 8 electron for this one. I'm just only writing the, this is greater than 16, so it will be like this. Okay, so 8 already done, then 2 and 7, 9 electrons are remaining. So 9 electrons we need to fill here. 2, then 2, then 2. How many? 6. Then how many are remaining? Then we'll have again pi anti-bonding 2px and pi anti-bonding 2pz. Okay, now 6. Okay, 6, 7, 8, 9. Okay, now it is going to have 2 electrons here. Okay, and here is 1. So they, how many bonding electrons are there? 1, 2, 3, 4, 5, any 10. Okay, are you getting my point?
Yes.
How many bonding electrons are there? These are in end 6. So 6 bonding, and how many anti-bondings are there? 2 and 1, 3. Okay, divided by 2, you will get 3, divided by 2, you will get 1.5. Okay, and if we're going to have bond order if it is not in the odd number, then it is paramagnetic in nature. Okay, got it? Or moreover, you can see here that it is going to have unpaired electrons, so it is paramagnetic in nature. Got it? So note it down. If the bond order is means, you can simply say that most of the time if the bond order is 1.5, then it is paramagnetic. So let's have a table here. Okay, let's have a table for which is paramagnetic and which is diamagnetic. Okay, so let's have a bond order trick. So if I'm saying number of electrons, then bond order, and then magnetic behavior. Okay, magnetic behavior. So if I'm just writing here that number of electron is, if it is 1, then bond order will be 0.5. only one electron, then bond order will be 0.5 because we will have 1 divided by 2. Got it? Then it will be, since it is not even, so it is paramagnetic. Then if we have total number of electron 2, then the bond order will be 1 and it will be diamagnetic. Then we have 3 electrons, then the bond order will be again. Bond order will be what? Don't think that it will become 1.5. Okay. Got it? So it will be the sum of these two. 3 can be written like 2 plus 1, 3. So it is going to have the bond order as 0.5. Okay. The difference of these two. Or you can remember it like this way. 3, then it is again paramagnetic. Got it? And total number of electrons are 4. 4 electrons, bond order will be 0. Why bond order will be 0 for? And it is diamagnetic because 4 electrons means helium, like helium structures. The 2 will be here in 1s2 and 2 will be in anti-bonding 1s2. So the number of bonding and anti-bonding electrons are same. So 2 minus 2 will be 0. Okay, now you understood? Understood? Are you getting my point?
Yes.
Yes.
Then if we are going to have 5 electrons, then 5 electrons will going to have again 0. 1 electron is added from 0. So 1 electron we have bond order 0.5, then it is again paramagnetic in nature. Then if we have 6 electrons, okay, then 6, then 4, then we'll have bond order 1. Then it is diamagnetic. Then if we have 7 electron, then what will be the bond order? Tell me. For 7 electron, what is the bond order? Tell me. 0.5. Okay. Then it is again paramagnetic. How? You can see. And if it is going to have 8 electrons, 8, then the bond order again will be 0. Why? Because you will say that 1s2 anti-bonding 1s2, then 2s2, then anti-bonding 2s2. Here the total number of electrons are 8. So they will cancel out each other. There will be equal number of bonding and anti-bonding electrons. So it will be 0. And for 0, it is diamagnetic. Okay. Got it?
Yes, sir.
So if we have 9 electrons, if we have 9 electrons, then there will going to be how many? So again 0.5 bond order for 9 because 0 for 8, again 0.5. You understood?
Yes.
Okay. Then again paramagnetic. Then if we have 10 electrons, then bond order will be 1. Then diamagnetic. If even sorry, no. Here we'll see that it is still paramagnetic. Why? For 10 electrons, it is still a paramagnetic in nature. Why? Still it has 10 electrons. So you can see here that for 10 electrons, 8 were filled. But if we are going to have a 10, then we will have like this one, 2px and 2py. And both will going to have 1 electron. So 8 were filled here and 2 will be filled here. So like this, 2px and 2py. So they are both going to have unpaired electrons. So the bond order is actually 1 because we have, okay, 2 divided by 2, you will get 1 bond order because the 8 will cancel out each other. The previous 8 will going to have the electronic configuration for it. So here it is so because the unpaired electrons are filled like this way. So we'll see here that the bond order will be what? Tell me. 1. Okay, for 11 electrons, the 11 electron will be filled like this one, like this way. So it is going to be the bond order as 1.5. And it is still paramagnetic. Why? Because here is one electron, unpaired electrons. For 12 electrons, we will fill the 12th electron like this way. So it is going to have bond order 4 electron, 4 divided, so it is going to have bond order 2. Okay, then it is diamagnetic, no unpaired electrons. Are you getting my point?
Yes.
Okay, for now tell me for the 13th. I'm just writing here. I'm just making the 12 electrons we have filled like this way. Okay, 12. Now the 13 electron, for 13 electrons we will fill like this way to 13. So we'll have 13 will have 2.5 bond order. Because there is no antibonding, electron is not going to antibonding. Okay, so it is 2.5, again paramagnetic, 1 unpaired electron. Then for 14, and it is going to have 3 bond order. 3, and it is not paramagnetic. Okay, it is diamagnetic. Got it? Got it?
Yes.
Yes, sir.
And for 15th, now this will be reversed for 15th. For 15th, if electrons are more than 14, then we have this type of electronic configuration. So 8 are filled in the previous one. Okay. It will fill like this. 1, 2, 9, 10, 11, 12, 13, 14, and then it will start going into the anti-bonding one. Okay. Anti-bonding. So tell me, if it is 15, what is the bond order? The electron will goes to in this one. Next electron. Now the bond order will decrease by 0.5 because it is going in anti-bonding, because anti-bonding electrons are increasing right now. Okay. So it will become again 2.5. Got it? Got it?
Yes, sir.
So it will be paramagnetic in nature at 2.5. Then at 16, it will be like this. Now again the bond order will decreases. And then again the bond order will decreases. Then the total number of electron will be, tell me, will goes into this one, and the bond order will be 0, 2.0. Then it will be again paramagnetic because there is unpaired electrons here. Then in 17, it is going to be again the next electron will comes to this way. Again the bond order will decreases with 0.5. 17th electron will come here. It will become 0.5 again. If still it is going to have one unpaired electron, it is paramagnetic in nature. Are you getting? Then in 18, it is going to be again next electron will filled here. And it is not going to have any unpaired electron, so it is diamagnetic, and the bond order will decrease further with 1. Okay. Got it? 17, you know. Okay. For chlorine, if you're going to have 18 for fluorine, okay. So it is diamagnetic in nature, no unpaired electrons. For 19 electrons, for 19th one, the electron will jump into this one. Okay. And when it jumps into this one, then again the bond order will decrease with 0.5. Okay. And here it is one unpaired electrons here, so it is paramagnetic in nature. And then for 20th, will have 0 bond order because it is also filled like this way and it is diamagnetic. Got it? Got it?
Yes,
You
sir.
can have
Yes.
this table. So for this table, you can learn each and everything properly. Now moving further, so this molecular orbital theory is going to help you to find out the bond order, to find out the paramagnetic nature for some elements or not. So if you can memorize this table, so for the 20th electrons, you can easily find out. Okay. Got it? So now
Yes.
moving to the next part here is, tell me the next question. If I'm going to have in which of the following magnetic behavior will change. Magnetic behavior will be changed. Will be changed means from paramagnetic to diamagnetic it can be, or it can be from diamagnetic to paramagnetic. So if I'm taking O2 to O2 minus, if I'm having N2 to N2 positive, okay, then O2 2 minus to O2 2 positive. And if I'm talking about B2 to B2 positive, tell me in which of the following the magnetic behavior will change. So you can write the electronic configuration. Total number of electrons here is 16, here is 17, here is 14, and here is 13. N2 positive, here is 16 already, 2 has been borrowed, so it is 18. And here it is 16 already, and 2 has been given, so it is 14. Then it is B2 10, and it is 1 borrowed, it is 9. Okay, So now you can check with the help of your table and then tell me which is going to have changing magnetic nature. So if the electrons are being changed, okay, N2, N2, 13, N2 positive, which one is you're going to see? Tell me.
N2, uh, uh, N2 is diamagnetic. When it changes to N2 positive, it will become paramagnetic.
Yes, it is diamagnetic because it is uh, okay, it is diamagnetic, it is fully filled orbitals, but when it loses, it will become paramagnetic in nature. Okay, 18 to 14 again, it will not change. Okay, this one, BE2, this is of s orbital is being changed, so this will not affect. So okay, so here means this is already paramagnetic, this is already paramagnetic. So in this one, it is going to change. Okay, so this will be the correct option. Understood?
Yes.
Okay, next is next question, last question for this one. Not last. Okay, if I am going to have when B2 is converted when B2 is converted into B2 positive, then A BB bond order will change or will increase. The second is bond order B2B bond length will decrease. Third, bond stability 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 will be increased. And fourth, paramagnetic paramagnetic nature will decrease. Which one is the correct? Done.
Option 3.
Option 3. Paramagnetic nature will decrease. Why? The option 4 is correct. You will see here that if we have a boron, so it is going to have 1s2, 2s2, and 2p1 electronic configuration. Okay. So here it is going to have in 2p, it is going to have one electron here, unpaired electron. So if it loses one electrons, okay, so now it is going to have bond order 1. But if it loses, so from 1 to If it loses one of its electrons, so there is one unpaired electron is being removed. So the paramagnetic nature will be decreased. This is correct. Okay. Since the bond order is shifting from 1 to 0.5, so the bond order is decreased, so bond strength will be decreased, bond stability will be decreased, bond length will be decreased, bond length will increase. Why bond length will increase? Because if the bond order is shifted from 1 to 0.5, then the repulsion of force will increase. Okay. And bond order will increase, bond order will decrease. So this is incorrect because bond order will decrease. This is incorrect because bond length will increase, because if the bond order decreases, the bond length increases. So it is opposite to the, this will also, stability will also decreases because it is, the bond is being shifted from 1 to 0.5. Okay, got it? Are you getting?
Yes.
Both of you, are you getting my point?
Yes.
Okay. So in the next class, this chapter is finished almost. Okay. And if you are having any doubt regarding to this one, then we'll discuss. Okay. So I hope you will be able to do questions regarding to this one also. Yeah, last question, if we take this question, the maximum bond length is found in Cn negative, O2 positive, H2 positive, and F2. So we'll find that this is very simple. The maximum bond length. Bond length means if the bond order is more, the bond length will be less. So find which is going to have the less bond length. So it is going to have one bond order. It is also going to have one bond order. It is also, what is the bond order of O2 positive? Check 15th electron. For 15th electron, how many? There will be 2.5.
2.5.
And for this one, carbon 6 and nitrogen 7, and one electron is being borrowed. So for 8. So you can have 14. So it is going to have 3 bond order. Now talking in this one, bond length, maximum bond length. So this is going to have minimum, then this one. Now comparing this and this one, you will find here that this is going to have more anti-bonding electrons as comparison to this one. So the stability of H2 molecule is more. So it is going to have very less bond length because its bond is very stable, because it is going to have no anti-bonding electrons. It is going to have anti-bonding electrons, so it is going to have one bond order, but the stability as comparison to as I have told you, if we have same number of bond order, then we'll compare the anti-bonding electron. So if the anti-bonding electron in F2 is more, the H2 don't have any anti-bonding electrons. It is going to have one S2, then one S2 only. It does not have any anti-bonding electrons. Okay, there's going to have only 2 electrons. So since it is going to have anti-bonding electrons, so it is going to have one bond order, but still it is less stable. So less stable, more bond length. Okay, so we're going to have F2 is going to have more bond length. Okay, this is the type of question that we're going to study in the next classes. So that's all for today. We'll meet you in the next one. I hope you enjoy the class.